So welcome back everybody to EE240. Hope you had a good break. So how many of you guys have actually, let's say, finished homework number 4? 1.5. Okay. Started at least? Okay, good. Any questions, issues, things people are running into?
Do we need to drive the load capacitance or?
So load cap is up to you. Right, so you're going to have a certain amount of capacitance in your system because of noise, essentially. But if you want to add that as explicit load capacitance versus as feedback capacitance, up to you. I don't care. Yeah.
What did you mean on the homework when you said somehow you went from 150 millivolts to 300 microvolts of settling?
Okay.
But, the percentage you gave us is 0.25%. Unless those two are.
So I think the microvolts was actually related to noise and not to settling.
No, because you had it wasn't in the spec list. It was the sentence right after. Let me go look it up. Sorry.
Okay, well, why don't we do this? Maybe we'll take it offline. If there's some typo there, then I'll post it on the web. But just come bug me afterwards, and we'll clarify that. Any other questions? Okay, well, so definitely, make sure you've gotten that well under wraps, because obviously it's due this Thursday, so Pierluigi will hold office hours and stuff like that tomorrow, but not a whole lot of time left. I guess we can count the hours almost. So definitely, make sure you get going on that, because again, it's a design problem, so it will actually take you some time. I guess you can ask the 1.5 people that are done how much time it took them, but again, make sure you kind of get going on that, because this is kind of a nice way to wrap together all the material we've been talking about so far. And very shortly, we'll actually have the project sort of up and posted that you'll be working on. So make sure you kind of get going on all that. Okay, so any other sort of questions on either the homework or material we've been talking about so far? Okay, so with that, what we'll probably do is sort of dive back in. We had gone through last time sort of this example design procedure, which we basically almost completely finished, but there was a couple of things that I wanted to just sort of wrap up with. And again, this design procedure was hopefully useful to you as you were actually going through the homework itself. So where we had basically gotten to last time was we had essentially completed the entire design, but there was just sort of a couple of things that I sort of mentioned that we would need to check. And in particular, the main thing was really related to the settling. So all the calculations we had done beforehand were really assuming that we essentially had a single pole settling. So really just the single pole. But in reality, there's at least sort of 2 effects that we were essentially ignoring there. So one is that we know we're going to have some feed-forward 0, and just to remind everybody, the topology that we're talking about is, of course, our standard capacitive feedback amplifier that looks something like this. So there's some CL, there's some CF, there's some CS, and of course there's some CI as well. All right, so this was the topology we were talking about. So we did all of our calculations and everything just assuming a single pole for this entire system. But again, just knowing that, of course, if I put a step right there, I'm also going to get a step at the output just to direct capacitive feed through. There was the feed forward 0 that we needed to worry about. Okay, and just to remind you guys sort of some of the values we were talking about here, this was 24 picofarads, this was 3 picofarads, our CL was 5.2 picofarads, and I believe the CI was roughly 1 picofarad. Okay? So, given that we had made this assumption about just it's a single pole and we can sort of ignore the feed-forward 0, the first thing we should do is just check, okay, how bad of an assumption is that? How much basically extra time would we need to spend to actually settle out due to that feed-forward 0? Which, remember, always causes you to do stuff initially in the wrong direction, and then you start settling in the right direction. So just kind of based on some of the values here, do you guys think that we're going to have a large impact due to that feed-forward 0, or no? Who thinks there will be a big impact? Won't be? Okay, why not? There's a bunch of people who obviously have no opinion, but at least the guys who said no, I agree with. So, what do you guys think? Why not?
Just because CS is so big.
Actually, that would sort of tend to push it the other way, right? So if CS is big, that means that VI right here should be pretty well coupled to this VIN right there.
ratio is like 1/8, like CF is to CL plus CF.
Yeah, okay, so actually it has more to do with CF relative to CL, right? So because CF is pretty small, probably not a whole lot. I mean, we may actually couple pretty strongly to here, but from there to there, there's a pretty reasonable attenuation, A. And as you said, the gain ratio is 8, right? The closed loop gain here is 8. So even if I sort of fully couple through there, only really 1/8 of the final swing would be sort of pushed you in the other direction. And so because CF is actually small relative to CL, it's even better than that in some sense. Okay, so that's really why this sort of feed-forward zero, at least in this particular example, probably doesn't matter too much. Now, that's not to say in general you can completely ignore it, but here at least, turns out not too big of a deal. Okay? So if we're sort of okay with saying, well, fine, maybe that's a minor tweak, that's within, let's say, a few percent or so, let's see if we need to worry about slewing. Okay? So now, in order to do that, again, we just sort of need to check that our assumptions were, let's say, correct. So I'd almost say this is like step number 10, let's say. So check if slewing is okay. Okay, so again, I'll just sort of repeat the drawing of the amplifier here just so that things are clear. So that's CF, CS, CL, and of course CI right there. Okay? So basically what we need to do here is we know we're going to have some input step that we're going to want to translate into a step at the output, right? If you remember, we had calculated sort of what the maximum swing at the output actually would be based on just the amplifier. So if we know what the maximum swing at the output can be, we also know what's the biggest step at the input, right? And if you remember, we actually used that to actually calculate how big this CS needs to be based on a sort of thermal noise consideration. Okay? So the reason why we want to know that is because obviously if this input step, the larger it is, the more we're going to couple directly onto that input of the amplifier initially, right? If we couple too large of a signal onto that node right there, that's when we'll start slewing. So what we really want to do now is just check how big is this input signal relative to the V star of the amplifier. Because if we actually couple an input signal larger than that V star, then we are indeed going to slew. Okay? So of course the simple way we can check that is just, and this is really just as a reminder of some of the numbers, the largest input step we can get is of course just the output swing divided by the closed loop gain, which turns out to be 120 millivolts. Okay? And if you just take those numbers that we had calculated for the CS and the CF and all these other things, it turns out that if I look at this Vx right here, then the largest step I can get on Vx turns out to be 107.1 millivolts. Okay? So now, by the way, why is it that this Vx is so close to this actual input step here? Why is it that those two are tracking each other so well? In other words, you know, there's like maybe like a 10% attenuation there.
CI is much less than CS.
Right. Basically, really it's CI in parallel with CF in series with CL. That whole thing is basically small in comparison with CS. Right? Because CS was 24 puff, and these were all like 3 puff, 1 puff, those kinds of range. Right? So it tells you indeed this Vx step tracks pretty closely with that input step there. Yeah. Which capacitance is what?
For the largest input step.
So remember, CS here is 24 picofarads. Okay, this one here is 3 picofarads. That's 5.2 picofarads, and CI is 1 picofarad, roughly.
No, I meant like which C is that referring to?
Which C is what referring to?
The C in the largest input step.
Oh, sorry, this is the closed loop gain. I'm just using the same terminology I had used earlier. Okay? So, now, as I said, we need to check whether or not this input step is large in comparison to the V star. Well, so if you remember, the input devices we had somewhat arbitrarily, but we had chosen a V star of 120 millivolts, right? So at least for now, looks like we're sort of okay from a slewing standpoint, because this Vx step right there is less than the V star of the inputs. Now, obviously, our model for slewing was a little bit simplified, so if you actually had something this close, it may actually be somewhat nonlinear, but at least it's not like grossly nonlinear, okay? So that's kind of good news. But if you remember, we had this sort of discussion at the end of last time about whether or not this was a good choice of V star. So anybody remember, what was kind of the discussion we had about whether or not we really liked this choice of V star, or rather, which direction we think we might actually want to push that to try and reduce the power consumption?
We over-designed it, made it too big.
Yeah, so actually, probably we made this a little bit too big, right? Because if you remember, we had assumed that CI was probably about the same as CF, but actually it's about 3 times smaller with this choice of V star. So that would tell us that we might actually even want to reduce that V star, right, to try and save some power. Well, what would be the sort of, let's not exactly problem, but what would be the issue that you'd have to worry about if you did reduce that V star to try and save some power like that?
Slewing.
Yeah, you'd slew, right? Because obviously 120 is not a whole lot larger than 107. So if you made this as an example, let's say 100 millivolts, because you thought that would save you about 20% in current, well, at that point you're going to start slewing. Right? So if you're actually slewing, you may not be able to actually reduce the V star all that much more. Okay? So in fact, this is exactly why, in your homework number 4, that second problem is for you to calculate what's the actual settling time when you are really slewing. That's actually exactly why you're going to use that expression. Because in cases like this, where indeed it looks like you may have wanted to use a lower V star, you're going to have to worry about what is the impact of slewing. If you don't know that, you won't be able to really pick what's the best bias current to use. Yeah?
I have a question. So, if you reduce the V star, your CI will increase, right?
Uh-huh.
Which means the ratio will reduce. Which means the Vx jump will reduce.
Fair, although notice that right now, this CI is much smaller than CF already, and it's even smaller than the series combination of CF and CL. So you're right, it'll reduce, but it may not change by that much. So you're right, this whole thing kind of shifts around a little bit as you move things around. But it's, again, really a question of sort of how big that ends up being, relatively speaking. So you're right, you may just get lucky and you never hit the slewing condition. But again, depends on exactly, obviously, the situation that you're in. It's a good question, though. Other questions? By the way, certainly, well, maybe not certainly, but likely if I was really aggressive and I made this, I don't know, 80 millivolts or something like that, good chance that you're probably going to hit some nonlinear behavior, even if the input isn't really hitting exactly V star. Because remember, our model for slewing was really, really, really oversimplified. Right? In reality, you're going to get something that probably looks like that and like that. Right? So you're going to start actually seeing some of the, not exactly slewing behaviors, but similar even earlier on. Other questions on this? Or yeah.
Increase V star. Is there anything else we?
Sort of. I mean, basically, it essentially means you need more bias current somewhere, right? Now, we may talk a little bit later on. There are some, let's say, more quote-unquote clever things you can do, like having things that have adaptive biasing. So things like Class AB amplifiers or Class B or etc. But basically, yeah, I mean, with our sort of methodology where we really want precise amplifiers, that basically means that you essentially have to either up the bias current, or you, at the very least, better include the effect of the slewing so you know what it's going to do to you and whether or not it's going to substantially change your overall settling behavior. Any other questions? Or?
It is okay to slew, though, right? I mean,
Yeah, it's not that you shouldn't ever be slewing, so to speak. It's just that, obviously, if you don't think about the fact that you're going to slew, then you're going to mispredict what's actually happening, right? Now, it may say that if you're really heavily slewing dominated and you just can't meet your settling time because of that, then, of course, you have to increase your bias current. And again, the only way you can actually answer whether or not that's the right thing is to have a model for what is the settling time as a function of the current. Good. Okay. So unless there's any more questions on that, that's actually basically it in terms of the example design procedure. And again, I think many of you are now sort of going through and coming up with your own design procedure, because that was, again, the entire point of the homework. But there's just one last sort of thing that I wanted to briefly mention, because it tends to cause a lot of confusion, even though at the end of the day it's a relatively simple thing. So in this whole thing, I was kind of talking about implicitly something that had a single-ended output. And so I was sort of talking about the whole amplifier as if it was a single-ended amplifier. But oftentimes we're in fact going to be dealing with differential and in fact fully differential amplifiers. So I just wanted to really quickly walk through essentially something that would tell us how do we compare between the two in terms of, let's say, SNR, or really signal swing and noise performance, and really power consumption, just to make it clear sort of what's going on there. Because again, there's a lot of times just confusion that comes up from thinking about it. So in order to do that, I want to basically draw two essentially equivalent amplifiers, okay? So first I'm going to have my sort of single-ended amplifier that essentially looks like this, of course with some V in and some V out right there, okay? And what I want to do now is compare that to the fully differential amplifier that's going to look like this. Okay? And this is, of course, VI plus, VI minus. And then, of course, I'm going to take the two outputs over there and have the two load capacitors here. Okay? So essentially, the intent here is that these two amplifiers are essentially identical, just that in one of them I'm sort of using two of them, or I should say in the differential case, I'm using two of the same amplifier to build a differential amplifier. Okay? So again, just to be really clear, because again, this seems to be a source of confusion in many places, let's just figure out what's like the equivalent signal power, or really the voltage squared that I can get at the output. So I guess I should be more precise. Let me actually call this like the RMS signal squared. Okay? So for that single-ended amplifier, just pretend I told you what the swing at the output is. The maximum swing, I mean. What would be the RMS voltage squared that I could get? So let's just say there's a V swing of output that you can tolerate at the output of the amplifier. What is the RMS for a sinusoid? What's it going to be?
1.5 V swing square.
Okay, almost. Just remember that if I can do an entire V swing at the output, the amplitude of the sinusoid is half of that, right? So I can do 1/2 of quantity V swing over 2 squared, right? Okay, I buy that. How about for the differential amplifier? What's that going to be? What is that V, the RMS, the maximum RMS swing I can tolerate at the output? Okay, there we go. So at that one, because it's differential, each side can actually swing by V swing, right? So when I take the difference between them, I actually get double the swing. So obviously I wrote this in a somewhat, I don't know, silly way, because I did 2 times V swing divided by 2. Obviously that's just V swing, but I just wanted to make the comparison clear. Okay? Okay, so it looks like I can get 4 times the mean squared voltage at the output. Okay? All right, so how about the noise? And again, I'll do this more precisely. Let me call that Vn squared. What kind of noise am I going to get at the output of this thing? And I don't need the exact expression, just, in general, when we have an amplifier, how do we usually quantify the input reverse noise?
Over C.
Yeah, there's going to be KT over CL, and then just times some NF, right? Okay, I buy that. All right, now, for the differential amplifier, how much noise are you going to have at the output? Somebody other than Shiva.
KT over CL.
Ah, I agree. Well, times NF, of course. But why 2 times KT over CL?
Because there's 2 devices and 2 capacitors. So
Yeah, so what's really the key there? Why is it that it sort of got, I mean, you're right, there's 2 devices, there's 2 capacitors, and you're taking the output as the difference between those 2 amplifiers, right? So why is it that the noise gets multiplied by 2?
They're uncorrelated.
Yeah, those 2 things are uncorrelated, right? The noise from this transistor is totally uncorrelated with the noise from that transistor. And so if I look at the voltage difference at the output, even though I'm doing A minus B, remember they're random signals, and so the signs don't actually matter. You're actually adding the noise powers together, okay? Now, by the way, just to be really clear, why did we not say anything about the noise coming from that I tail? Why is that not counted?
common mode.
Yeah, it's common mode. In other words, it's correlated between that side and that side, right? So now when you do the subtraction, the sign actually does matter, okay? So just remember, keep that in mind, because with all those calculations of noise and stuff like that, it's really easy to either square too early or square too late, okay? Or I should say really take root mean squares too early or too late. Okay, so far we've got 4x of the signal swing squared, 2x of the noise, right? So of course, if we look at the SNR for this, it's just going to be something like, and let me just get the numbers right, yeah. V swing squared over 8 divided by KT and F times CL, right? Okay, and so here, we're actually going to get, if you just work that out, it's going to be V swing squared actually over 4 divided by KT and F times CL. In other words, we actually have twice as much SNR in the differential amplifier as we do in the single-ended amplifier. Right? Because notice, this went up by a factor of 4, and the noise only went up by a factor of 2. Okay? Yeah?
But the MF should be different for both, though.
Why?
There's more transistors on the right side.
Well, we just said that this guy right here doesn't contribute any noise, right? So if this is a virtual ground right here, and I arranged it so that the V star of these 2 transistors is the same as the V star of these 2 transistors, and the voltage drop across these 2 current sources is the same as this current source, then actually the NF should be identical, right? Now you're right that really if these were exactly the same supply voltage, the voltage across each of the transistors would be a little bit different. But, you know, bear with me, pretend somehow I had a negative supply or something like that. Okay? So in other words, I'm really trying to make it so that this whole piece right here is the same as that piece right there. In other words, if I just, you know, kind of drew a dotted line around this, saying take all the voltages and everything and make it identical to that. Okay, in that case, the NF should really be the same. Does that make sense? Or? Okay. Okay, so looks like magic, right? I got twice as good SNR by making it differential. So is this really magic, or what's going on? What am I? There we go, exactly, right? So no magic here, because in fact, if I look at the power, that's of course just VDD times I bias. Well, of course, over here, it's just going to be 2 times VDD times I bias, okay? So the reason I walk through this whole thing is just to make it really clear that even though there's lots of different, you know, sort of confusions associated with this, there's no sort of magic really happening with differential. You get twice the SNR for twice the power, which is exactly what you could have done in the single-ended case as well, okay? It's just obviously arranged in a slightly different way. So just to be clear, really the only reason you want to do something like this is oftentimes that you want to reject common mode noise. Okay? You want to be able to just ignore things that you know don't really have to do with the signal. Okay? And of course also if you do something like this, it's much easier to figure out what differential 0 is, versus here you always have some biasing thing that sort of sets you away from what really 0 actually is, at least in voltage. Okay? Does this make sense to everybody? Or? Okay, so just kind of keep these things in mind because again, you're doing your sort of design procedure now for a single-ended amplifier, but I very easily could have made it a differential amplifier, and I would claim that basically nothing would change. You just have to be a little bit careful with keeping track of which quantities you're talking about that are single-ended versus differential, and what the swings are, and what the noise is, and etc. Okay? Any other questions on this, or? Okay. So, unless there's any other questions, then let's actually go ahead and move on to really the next topic, which we really actually sort of hinted at even before this, which was, okay, now we've talked about how to build these amplifiers. We sort of mentioned how we really do want to build differential amplifiers, because again, we want to be able to reject common mode noise, power supply noise, things of that nature. But there was one issue that I mentioned, for you to pay attention to, because it often comes up, for example, in like interviews or prelim exams or things like that you'll often care about, which is whenever you build a differential amplifier, don't forget about the common mode, okay? So today what we're going to spend a little bit of time talking about is actually how would you really build active circuitry to try and control the common mode, okay? So, oh, that's actually old stuff. Don't worry about that. Okay, there we go. So just to be sort of really clear as to why all of this is important, let's just do sort of the following thought experiment. And so here I'm going to do this with a fairly simple telescopic amplifier, but the same thing applies to a folded cascode or just about any other amplifier you can think of, okay? So let's say this is my differential amplifier here. And let's just say from whatever reason, somehow, there was some mismatch, or I just, screwed up my layout a little bit. And so I went and I built this amplifier. But so that rather than I tail being exactly equal to 2 times this I load over here, somehow I got a little bit of extra current flowing through here. Let's say, I don't know, 10 microamps or 1 microamp or whatever it is. Okay, so I just got a little bit of extra current flowing through there. So if that was to happen, and really everything that I drew here was correct, in other words, I really had current sources for my loads, what would these two output voltages be? Where would they go to? Just DC, where would they be sitting at? This is not a trick question, by the way. Where would those go to? Come on, somebody must have an idea here. Yeah.
Ground?
Yeah, it's going to go to ground, right? Because you put in a little bit of extra current over here. That little bit of extra current flows through a open circuit load, right? So guess what? It's going to go straight to ground. Okay, so are you going to be very happy with an amplifier with NMOS transistors with the drain to source basically being 0? No, right? Not going to work, not going to do squat. Okay? So the point is here that even though this is a common mode error, obviously it can completely screw up the biasing of your amplifier, right? And by the way, my example here of this being 10 microamps or 1 microamp or even 1, well, maybe not picoamp, but let's even say, depending upon how high your impedances are, really could cause you to actually land in the wrong spot. Okay? In fact, not only could you mess up the biasing of your amplifier itself, maybe this goes so far down that the next stage can't actually get it out either. Right? Maybe you actually shut off the NMOS transistors of the next stage. Okay? So clearly this is something you're going to have to worry about. Now let's actually maybe do another thought experiment. So let's say, okay, well fine, the amplifier by itself maybe is a little bit screwed up, but what if I tie this thing into feedback? Because usually I'm going to take my fully differential things and I'm going to tie them into feedback, right? So let's say as an example, I tie it into capacitive feedback just like we've been talking about sort of all along. So let's say I do something like that. So now here's the interesting question. Will that capacitive feedback solve this common mode problem? In other words, that if I have a little bit of extra delta I here, will it force the output to sit at some nice spot, or no? Who thinks it does solve the problem? Raise your hand. Doesn't solve it? Okay, at least based on my tone, you should be able to do better than that. So who thinks it doesn't solve it? Okay, good. So now, why? Why doesn't it solve it? What's the problem?
DC biasing?
DC biasing. What do you mean by that?
I don't know.
Oh, okay. No problem. Are you just saying these are capacitors and so it ignores stuff at DC?
Yeah, that's what I was saying.
Okay. Well, that's a good guess, although that's not exactly it. I mean, you're right. These are capacitors, and so if at DC these things are wrong, the caps don't do anything. Let's even pretend I did this with resistors. So let's even pretend I did something like that. Okay, so we'll knock that problem off. I'll still claim that there's something not so great about this. So let's maybe actually just walk through just to be clear. So if the common mode changes, as an example, let's say that both of those sides go up, what's going to happen on these two gates right here? Just due to the feedback, which direction is that going to move? Up or down? Yeah, it's going to move up. Okay. So that actually sounds good, right? Because if those move up, if these were just really, if this was really tied to ground right here, then actually life would be very good. Because then I'd be pulling some current back down out of the output, right? Okay, so now, what is really the problem? Why is it that I don't actually do that?
The pair can't change I-tail. Right?
Yeah, exactly, right? Essentially, if I really had an ideal I-tail right here, then the whole point of adding this thing in the first place was to make it so that whatever common mode input I put directly on those gates there gets rejected at the output, right? So even though I've got a differential feedback loop with a reasonable amount of gain in it, common mode, because of that I-tail, I have no gain, right? Essentially, maybe I will get a tiny little bit of current, but it'll be really, really small. It'll just be because of the output resistance of that I-tail right there. Okay? So bottom line, what this basically tells you is if you really, well, actually, in fact, you almost always do, if you actually want to set the common mode, you in general can't just rely on the differential feedback. Because 90-something% of the time, you're going to set the differential feedback up, or you're really going to build the differential amplifier in a way that you're intentionally rejecting common mode noise. And if you do that, that basically means anything that happens to couple back to the input as common mode, you're intentionally going to try and reject. Okay? So that basically means we need to build something that really is explicitly going to try and control the common mode at the output. Okay? And so, of course, what's that called? What people basically refer to that is essentially common mode feedback. So what that really means is that somehow we have to sense the common mode at the output and then use that to adjust some knob to alter the common mode at the output. Okay? So your sort of classic feedback. You sense what the problem is and then make an action to correct it. Okay? So what I'm going to do is actually first sort of walk through how would we go about sensing the common mode problem. And then I'll just mention a couple of sort of typical knobs we can turn. And then I'll talk a little bit about sort of practically how would we really build these types of feedback circuits. Okay? So let's just start out with sort of the simplest common mode sensor that you can kind of think of. Okay? So remember, common mode, what you're really trying to do is look at things that are moving basically both on the plus side and on the minus side. Well, so it turns out the easiest way for you to do that is pretty literally just take two resistors, tie them across the differential, and then look at the middle point. Okay? Because if you sort of think about it, if these two resistors are really the same, then anything that's differential, this point right here is a virtual ground, right? Because if I go up by, let's say, 10 millivolts on the left and down by 10 millivolts on the right, the center point should do nothing, right? Of course, if both sides were to move, then now, obviously, that center point also has to move, right? Because there's no current path back to ground through that. So if I measured this voltage right there, that of course has to track with the column mode at the output. Okay? So that indeed is the sort of simplest thing you can think of, but just like with the differential feedback, or the sort of classic feedback we had talked about, if we do this with an OTA, it's a little bit bad news, right? Because basically adding those resistors on, now remember we said that differentially speaking, this was a virtual ground, right? If that's a virtual ground, then that means that those resistors there just look like a load resistance, right? In other words, your gain would effectively just become the GM of the input devices times that load resistance, okay? And in fact, by the way, a lot of times, if you wanted to build an amplifier where you can control the common mode independently of the resistance, this is in fact exactly the way you would do it. Okay, you'd have some sort of active load, and then you'd put a resistor across the terminals to set that essentially differential gain. Okay? Okay, so now we're sort of back into our classic stuff that we had talked about with the normal feedback, right? So essentially, if we put these resistors across here, then it's going to load our amplifier and reduce the DC gain. Okay? So just like we had said before, okay, well, fine, maybe if we don't want to reduce the DC gain, we'll just try and make these really big. Okay? So we'll make them like, I don't know, a giga-ohm or a tera-ohm or something crazy like that, just so that they don't really mess up our output impedance from the amplifier. Okay? Well, so again, that all sounds nice and dandy. But now, remember, if I'm going to build some sort of common mode feedback, what I basically have to do is take that node over there, and somehow I'm going to be building another amplifier that's going to be looking at that thing, right? Well, guess what? That amplifier is always going to have some capacitance associated with it. So now, what's the bad news that's going to happen if I have essentially a tera-ohm of resistance right there? And I don't know, let's say even 10 femtofarads of cap right here. What's the bad thing that's going to happen?
Really slow.
Yeah, it's going to be really, really slow, right? Okay, so now why is that bad? Why is it bad that the column mode feedback is really, really slow? Why might you care about that? Or why might you not want that to be the case?
It's changing very fast and it's not doing anything at all.
Yeah, right? So if I happen to get any fast column mode glitch, then my amplifier is not going to do squat to correct it. Or really, my feedback loop is not going to do squat to correct it, because it's just way too fast for the feedback loop to actually handle. So now, by the way, do you expect that you would get fast column mode changes? What do you guys think?
For a switch cap amplifier,
Okay, as an example, yeah.
Yeah.
Okay, why?
your clocking changes into the amplifier.
Okay, yeah, right. I've got some clocks flowing around in the system. In fact, if I'm building this as a switch cap amplifier, then right in the phase where I start amplifying, right, I'm going to be putting essentially some glitches into these inputs right here, right? And hey, okay, my current sources are nice, but they're not perfect. So actually, some little extra glitch of current is going to flow into the power supply, right? Okay, that little extra glitch of current flowing into the supply is obviously going to cause some voltage ripple, right? So in fact, if you actually look at what usually happens if I looked at like a differential input, right, usually what actually happens is that, you know, the inputs may be doing something like this, which if you look sort of carefully at how I've drawn this, would mean the column mode is actually has some glitch like this, right? Well, so if your column mode feedback is too slow to even pay any attention to this thing, if that glitch is big enough, it could mess up the bias point of your amplifier. In fact, perhaps even worse than that, remember you usually have, you know, in really high gain amplifiers, if you have a differential mode gain of, let's say, I don't know, 10,000, you might still have a column mode gain of, I don't know, 100 or so, right? Or maybe even 10. Well, if I still actually have a column mode gain of 10, that means I'm going to be taking that small little glitch and amplifying it up, right? So if I feed this into another stage, even though I have a good ratio between differential gain and common mode gain, the next stage may already see something large enough that it goes out of whack, right? So bottom line in general, you actually want to make your common mode feedback loop, and of course, I'll show you in a second how we really close the whole loop. But in general, you really want to make your common mode feedback loop basically track the dynamics of your overall amplifier. In other words, you want to make that loop have as high of a gain bandwidth as your actual amplifier does. Because again, if you don't, what may happen is that because of the common mode not being settled, you may actually see some differential settling components that dominate the performance of your amplifier. Okay? So in general, make the common mode feedback basically as fast as your actual amplifier itself in the differential mode. Now, the good news is a lot of times that doesn't necessarily cost you a lot of power. So, and we'll see sort of how we'll actually do that. But, you know, as a general design rule, you should definitely keep that in mind. Okay? Okay, so we've kind of said resistors, we can kind of make it work, but it's a little bit annoying because in order to make them big enough to not load us, basically slows down the loop. So we'd like to be able to come up with, obviously, other sensing schemes. And of course, there's a bazillion different sensing schemes people have come up with. So here's another one just as an example. This one actually works reasonably well. The idea here is that rather than sensing it through resistors, I'm basically just using two source followers and then tying their outputs together. Okay, so it's kind of like I'm building a little buffer to sense each voltage individually. But then by adding the two buffer outputs together, really in the current domain, I'm getting like the average voltage, which is really what you want when you want the common mode. Okay? So this works reasonably well. I mean, I don't have to load the output of the amplifier anymore. But you have to be a little bit careful. Because I'm building these sort of source followers here at the output, I may actually be limiting the swing I can tolerate at the output of this amplifier right here. Because if you think about it, at least on the low end, this current source right here is going to need basically a V star across it, right? Similarly, that source follower there is going to need a V star plus actually a VTH for the VGS, right? So that basically means that the lowest voltage I can tolerate over here is 2 V star plus VTH, okay? If I go any lower than that, basically the transistor will be off and this whole common mode sensing really won't work anymore, okay? So again, although this works sort of reasonably well, it's not going to be so great in something where I really want a wide swing at the output. And remember, in general, you're going to want as wide of a swing as you can get, simply because that's the way that you're going to get effectively better SNR. Okay? So again, maybe not the sort of best solution for our, let's say, general OTAs. Okay, so what do you guys think? How are we going to solve all these problems? What's going to be the magic sensor we're going to use? Give you a hint. We sort of did that transformation once already.
Capacitors.
Yeah, exactly, right? So even before we said we didn't like resistive feedback, but capacitors, we kind of argued our way into why we needed capacitors anyways. So guess what? Same thing. Rather than using resistors, we'll use capacitors to do the sensing. Okay? So again, for same reasons as before, this is good news because now we're avoiding any DC loading. Right? We're not going to change the DC gain of the amplifier, which a lot of times we're working so hard just to get that gain of 10,000 or 3,000 or whatever it is. Okay, so that's good news. Of course, the bad news is if I add these caps in, I'm still going to create some sort of AC loading. But again, if I needed those capacitors for noise reasons in any case, I can kind of just allocate some amount of that cap to be for these common mode sensing rather than for example, just sitting there as load cap like that. Right? So basically all the same arguments we made before about why capacitive feedback basically works in our context, same thing happens here. Okay? Now, there's just one sort of, let's say, minor, quote-unquote, detail we need to deal with here, which is, and maybe I'll even ask you guys, so if I look at this voltage right here, am I actually sensing the real common mode? Or am I sensing something else about the common mode at the output of the amplifier? The actual output of the amplifier, I mean. What am I really sensing by putting these capacitors here like this?
An integral? The common mode, sort of?
Not quite. I mean, if the common mode was in current, then you'd be right. So I'm thinking of the common mode in voltage over here.
Yeah, attenuated version.
Okay, there's some attenuation there. I agree with that because maybe there's some cap here, but don't even worry about that. What am I really sensing when I do this?
Charge.
Okay, that's, I mean, charge, but so what is that related to in terms of the voltage, I guess?
Differential.
Ah, somebody said differential. Why differential? By the way, I agree with you, so whoever said it, you should, you should be proud of yourself. You're basically sensing the change in the common mode, right? Because as an example, let's say that somehow magically at the beginning of time, I told you that this was 10 volts. I don't know how it got to be 10 volts, I just decided it's 10 volts, okay? Right? And that this was, let's say, I don't know, 0.5 volts on the common mode, right? The capacitors can't do squat to change that, right? They can't do anything about this 10 volts that's sitting right here. The only thing they can tell you is if this moved up by, let's say, 10 millivolts, then yeah, okay, fine, that'll go to 10.01 volts, right? So again, just like with the switch cap amplifiers we were dealing with before, use capacitors for the feedback. You essentially have to do something to initialize them. Because what you're actually sensing is the change from an initial point. And if you don't know what that initial point was, then obviously that initial point is sort of arbitrary and anything can happen there. Okay? So just like before, we need to do some sort of reset on these capacitors to make sure that we're really sensing the instantaneous common mode. Or really just to make sure that we're actually sensing, that we don't have some arbitrary offset that's been built into this thing, which is kind of what we were trying to avoid in the first place. Okay? Does this make sense to everybody? Or? Okay, so we're going to take a look in 1 second at sort of solutions that really use this capacitive feedback. But before I do that, since we talked about the sensing side, now I want to talk about the adjustment side, or what's really the knobs you're going to turn to try and control the common mode. Okay? So the good news is here that really there's kind of only two knobs you can turn, right? There's sort of only two adjustments you can make to try and change the common mode. Either you can essentially adjust the load current over here, or you're going to adjust the tail current, right? So for either one of them, if you keep basically one of them fixed and you adjust the other one, or vice versa, that's basically how you could actually make an effect on the common mode at the output over here, right? So that's good, that's pretty easy, and in fact, to do this, we'll see in a second, doesn't even really require all that much change over what you might have done anyways. So let's actually just take a look at an example of how would you use one of those two knobs to basically build an actual common mode feedback circuit, okay? So here I'm not actually doing, really exactly what I said I would, because you'll notice that I'm actually using a resistive sensor right here, but you can even pretend that's capacitors. Okay, we'll come back to that actually in 1 second. So just to be sure that it's clear, all that I'm doing here is, if the common mode changes, meaning both of these go up, then this VCM over here, of course, is just going to track with that, so it's going to go up as well. So then all I'm trying to do by adding this amplifier in here is I'm sensing that change relative to some reference common mode that I want. And then I'm going to make a change at the gate right here to try and counter that change in common mode. Okay? So now, just to make sure that everything is clear, if you'll notice, usually people like to draw the feedback as being on, the negative terminal of the op-amp. And this time I drew it on the positive terminal of the op-amp. So, did I do the right thing or did I mess up? So did I tie this up really in the way that I want it to be tied, or is this going to be a problem? No, no, I didn't tie it, or no, I did tie it, or what do you guys think? Said another way, is this really negative feedback right now, or is it positive feedback?
The feedback.
It's negative feedback. Why is it negative feedback?
Because the output is at the gate of the current source, and the current is a negative feedback.
There you go, bingo, right? So if this thing goes up, the way I have it tied now, that VBP would go up, right? Which then means, and I'll draw it in a different color just to be clear, because this is a common source amplifier, the change at the output would be negated, right? So in fact, I really did tie this thing up the right way this time around. That's not to say that I always do it, so if you're not sure, you should check for yourself or ask me. But this time I did actually tie it the correct way, okay? So that's basically how this thing is working. I'm taking that sensing and I'm just tying it into a negative feedback loop by changing these load currents right here, okay? And as you can imagine, if I really have some high gain amplifier right here, this is just going to force it so that VCM should be equal to whatever this reference is. Right? So it's just going to adjust these currents until those two are equal to each other. Okay? Now, by the way, of course, this is a real feedback loop, right? So anytime you have a feedback loop, you have to worry about stability, right? Just name of the game. So, if I have to worry about stability, then what I basically have to think about is where are the poles in this feedback loop, right? So, you guys tell me, where would the poles, how many poles actually first, and where would the poles be in this particular feedback loop here? What do you guys think?
There's one at the gate of the current sources.
Yeah, so I've definitely got one pole right there. Where else am I going to get a pole?
VCM.
Yeah, I've definitely got another pole right here, because of course there's some cap right there. And there's some resistance driving that cap. Just to be clear, are there any other poles?
Drain on the PMOS.
Yeah, so there's kind of a pole right there, right? Now, the good news is if you've sort of done things, let's say, well, probably it's either this pole or this pole that you're going to be really messing with when you build this common mode feedback loop. Because this pole over here from the PMOS, that's kind of the amplifier itself, right? That's the differential part of the amplifier. Now, building this common mode feedback loop, you don't want to be messing around with that. Right? That's the other, okay, it is your job to build the amplifier, but that's like the other compartment of your job, right? That's the differential side of your job. This is the common mode side of your job, okay? So now, for this common mode feedback loop, where do you think you're going to want to put the dominant pole? So do you want to put it at P1, meaning at this gate of the bias transistors here? Or do you want to put it at P2, meaning at that sense point? What do you guys think? Who wants to put the dominant pole at P1? 2.5, 3 brave souls. Okay. Who wants to put it at P2? Well, you got to put it somewhere. I'm going to start throwing stuff at you. So who wants to put it at P2 now? Okay, another 2 brave souls. P1. Okay, slightly more brave souls. Okay, so those of you guys who wanted to put it at P2, why do you want to put it at P2? Other than I was going to throw something at you. Any thoughts?
The sensing resistors will be pretty large, so which means the pole will be at a lower frequency.
Okay, I guess I agree with that, but so if this pole is at a low frequency, what does that mean about this pole? In order for you to be stable.
It should be higher.
Yeah, so P1 better be higher. How do you make P1 go to a high frequency?
You need to reduce the size of the PMOS. Or
Can you do that? Remember, you're in the common mode compartment right now. So can you change the size of these PMOSs? Probably not, right? Okay, so what do you have to do to make P1 be fast?
Increase the
Sorry, what were you saying?
Lower the output impedance.
Okay, I have to lower the output impedance of this thing. How do you do that?
Stage.
Okay, you could add a buffer stage. What is, and so by the way, you know, I'm a, let's say, power bigot, so I always worry about power. So what does adding a buffer stage actually mean? You gotta spend more power, right? So in order to make this thing be high enough frequency, that basically means I need to jack up some sort of I bias in there, right? I'm not so sure I like that one. So, you know, thank you very much for being brave, but, you know, unfortunately the slightly more popular choice turned out to be the right one. Or at least I think probably the right one in this context. Okay? So, if I had instead actually made P1 dominant, right? Okay, so everything you said is correct. You know, you have to make these resistors large, you can't have too much cap here, but let's pretend I actually fix that. I'll make this a capacitive sensor instead. Something like this, right? And I just take some of the cap I needed anyways to do that. I would actually claim you really want the dominant pole to be right there at P1. Because notice what's creating this pole here is essentially just how much power am I spending in this amplifier, right? And so if I end up spending power in this amplifier just to make the whole loop stable, that kind of sucks, right? I'd much rather just spend as little power as I possibly can here, make that the dominant pole. Still, I have to spend enough to make the overall loop fast enough, but I spend just enough to do that. And then I just be careful about this node right here to make sure that it always is at a high enough frequency, right? So actually, if I had the choice, I'd really rather make P1 be dominant. Just because, again, moving P1 around directly costs me power. Whereas P2, maybe not, right? Maybe I can actually be a little bit clever into how I choose things so that that doesn't change the amount of power I spend. Does this make sense to everybody, or? I see some somewhat confused looks, so I'm going to wait until I get a question. Eric, you look like you must have a question. No? Okay, well, so again, really the key point here is only that the pole for this feedback loop right here, at least the pole coming from the amplifier, that's really just directly being set by the bias current, right? Because the output impedance, or even the GM you get from this, is just directly related to the bias current. So what you really want to do is choose that bias current based only on the overall gain bandwidth you need, but no more than that. So once you've chosen that bias current, that sets this pole somewhere. That sets the dominant pole somewhere. And then you just have to make sure that this pole right here is far enough away that it's not going to screw up the stability of your overall loop. Okay?
I have a question.
Yeah, good.
So if the common mode bandwidth is comparable to the differential bandwidth, seems like you could get into trouble there. I mean,
You're just worried about, for example, the common mode somehow coupling in the differential and vice versa?
right.
You're right, although in general you're really trying to build this amplifier so that they're sort of as decoupled as you can make them, right? And in fact, actually that sort of brings up a good question. So if I really do have this common mode feedback loop here, and let's say that somehow magically I build this thing to have like infinite DC gain, okay? So if I do that, what would be the common mode rejection ratio of this whole amplifier? And by common mode rejection ratio, just to be clear, I mean the ACDM divided by ADM. At least at DC. What would that be if I really had infinite gain inside of this op amp right here? Sorry, actually, be more clear. Let's actually just do the easier one first. Let's just make it ACM over ADM. What would that be?
ACM should be 0, right?
Yeah, right? Because if I have a perfect common mode feedback loop there, let me just erase a few things here to make it more clear. So if I have a perfect common mode feedback loop here, what that's basically doing is forcing the output common mode to be VCM ref no matter what, right? So if I do that, that means that any change in the input right here should correspond to 0 change in the common mode at the output right there, right? So if I do this, I basically have, let's say, infinite common mode rejection, at least from the standpoint of ACM over ADM. Now, even if I then look at ACDM over ADM, now, right, where's sort of the only place that I could be picking up some sort of mode conversion from? What's the only way that I can sort of get an error?
Match or
Yeah, it'd have to be some sort of mismatch, right? In fact, it'd probably have to be some sort of mismatch on the input pair right here, right? Because by building this common mode loop, I'm forcing this common mode to be sort of dead pinned, right? So it'd have to be some sort of mismatch between either these, or in fact, actually, as we'll sort of see in 1 second, if I have some sort of mismatch between these two, then maybe I'll actually pick up a little bit of conversion between them, okay? So actually, but again, sort of, just to take a step back and make sure everything is clear, the main point I wanted to make here was really just whenever you do these sort of common mode feedback loops, what you really want to do is you want to set the thing so that the dominant pole is at the point where you sort of naturally have the highest impedance. And the point where you're naturally going to have the highest impedance, in general, is going to be where you have to spend power, right? Because that's where since you don't want to spend power, that's going to be as high of an impedance as you can basically get, okay? Okay, now, so this does actually bring up one good point, which is that if we pay attention to this thing, and actually I'll draw it over here, if we pay attention to this, as we'd said, the way we get sort of conversion from changes in the common mode to changes in the differential is by introducing a little bit of mismatch, right? So in particular, what would happen if, let's say, these two PMOS transistors are ever so slightly different from each other? What would happen then if I put a purely common mode input over here? What would happen at the output? What do you guys think? So first of all, what would be the ACM for this? And again, let's assume that this has infinite gain right here.
feedback should still force it.
Yeah,
Zero.
ACM's still 0 here, right? Because as long as that feedback loop has infinite gain, then, and as long as these two resistors, of course, are perfectly matched to each other, then I'm going to force the common mode to stay exactly where it was before. Okay, how about ACDM? Is that going to be 0 or no? Ain't going to be 0 anymore, right? Because as soon as that common mode input goes up, this goes down a little bit, this goes up a little bit, and so now, oops, I take this small voltage signal, it's going to translate into two slightly different currents, right? So over here it's maybe I, and over there it's maybe I plus delta I, right? Well, guess what? That means I'm going to have a differential change at the output, okay? So one thing to sort of pay attention to here is that when you do these common mode feedback loops, you could actually be creating extra differential conversion. Simply because now that you're moving this thing around, if there's some mismatch in the characteristics of these two, you're actually going to be amplifying that change over here into the differential mode. Okay? Now, there are some tricks you can play to sort of at least mitigate this somewhat. And I'm just going to draw the example of how you might do that. Or actually, maybe I'll ask you guys. So let's say that this is my gate voltage that I'm adjusting. So remember, the whole point of doing this was that I just wanted to change the common mode current at the output. So if I just want to change the common mode current at the output, at least in principle, what would be sort of one way I could, let's say, modify this circuit so that by moving that VCM adjust, I'm going to change a common mode current going into the circuit. What do I sort of have to do here? So it's, by the way, we'll call this I1 and I2. So just to be clear, what is the common mode current?
I1 plus I2 over
Yeah,
2.
it's I1 plus I2. So how can I make it so that if I1 and I2 both sort of change slightly differently, how can I make it so that, the whole thing is just common mode?
Like the drains.
Yeah, I'd have to tie the drains together, right? By the way, tying the drains together means that I'm forcing the whole thing to be I1 plus I2, right? Okay, so now there's, of course, a minor problem, which is that I still wanted two different drains, right? I still wanted two different outputs. Well, okay, so the way I would do that to actually get two different outputs, this is an example. You can add cascodes with two different drains over there, okay? So in other words, this would now be like a fixed V bias, okay? So the idea here is actually kind of simple. At the point where I'm making the adjustment, I'm tying everything together and forcing that to be common mode, and then only afterwards splitting it out into the two different branches. Now, you have to be a little bit careful here, because obviously, even though I've made all the adjustments together at this point right here, I still eventually have to split into two different pieces. And as soon as you do that split, if there's some errors on these two, then again, you might actually amplify that common mode change into a differential change, okay? The reason I only even mention this is just that potentially by doing something like this, you might be able to design these transistors to match better than those transistors. As an example, you might be able to change the V star on these devices without having, for example, an implication on the noise coming out of the transistors, okay? So this is really more, don't worry too much about this particular solution because it's not necessarily, the most straightforward one. But the idea here is just in general, anytime you have a common mode feedback loop, just be careful that you don't actually create extra differential conversion, okay? Because again, now that you have stuff that's changing, you might actually be amplifying into the differential mode because of mismatch in the system. Okay, so we've kind of beaten, the adjustments off to somewhat to death, let's say. And we've so far been looking at sort of the resistive version, but as we sort of motivated a few times already, the resistive version maybe isn't the best one to do. And we actually so far we've been looking at adjusting those knobs right there. But as we also just said a second ago, well, maybe these knobs aren't necessarily the best because I kind of want to just change one thing, right? I want to change just the single point and then have it show up on both sides for the common mode, right? So here what I'm actually going to show is essentially, it's really kind of the same idea. Just now it's going to be using capacitive feedback rather than resistive feedback. And again, this time I'm going to adjust a slightly different knob. So I'm going to adjust essentially the voltage at the tail transistor instead of on the load transistors, okay? But really, actually, I want to take a look at this particular version A because you can see this is actually a pretty simple thing to do, right? But B, actually, it's also going to sort of tell us a little bit about just sort of from a design procedure, what are some of the issues we need to worry about in terms of doing this common mode feedback, okay? So just to, again, make sure it's sort of clear, before when we built the sort of capacitive sensor, we said there was some center point that we called like VCM. I'm really doing that same thing here. It's just that I've tied that center point onto this V bias for the gate of the transistor right here, okay? So really just to be sort of clear, this thing over there is essentially something that looks like that. Right? That's basically just our standard, diode-connected transistor driving the gate to mirror over a current, okay? So again, just to be clear as to how this whole thing works, of course, if the common mode over here moves up, this is going to move up, and you're going to pull down some current through there. Okay, so it's basically our sort of same common mode feedback loop that we looked at before, just that now there isn't an explicit amplifier taking the sense signal and driving it back onto the gate right here. Or just by tying the sensor onto here, we're directly coupling that voltage change onto the gate. Okay? So now if I was to do something like this, there's kind of a couple of, I guess, interesting questions or really trade-offs that we run into here. Okay? And in some sense, the first one is really, how would I go about choosing the size of these capacitors here? These capacitors for my sense circuit in particular. So in order to answer that question, we sort of have to look at really sort of two things. So the first is, as I change the size of these capacitors, what I'm basically going to be doing is changing the gain from the actual common mode voltage right here to the gate of my bias transistor right there. Right? And by the way, just to be sort of clear, usually if you do something like this, there's a big resistor right there just so that basically the common mode couples freely onto that node at any frequency of interest. Okay? So now, just to be clear, if I was to draw this whole thing kind of with my standard model, let's say, and actually let me maybe even, yeah, I'll do it this way. All right, so what I'm basically doing now is something like essentially this. Yeah, we're going to come back to that actually in 1 second. So you're absolutely right that if I'm doing this, obviously this capacitor doesn't do anything about the nominal bias point there, right? So you'd have to somehow make sure that this nominal bias point, either you'd reset it or something like this, and we'll see an example of that in 1 second. Okay? But so just to sort of walk through it really quickly to see sort of how we'd size this thing up. If you sort of think of the model as being like this, if I look at the change in common mode at the output, what's going to be the gain from that point to this input common mode point right here? What is that gain going to be set by?
CM over CM plus CGS.
Yeah, exactly, right? That gain is just going to be set by CCM divided by CCM plus CGS, right? In other words, if we make this CCM small, then this gain feeding back onto the gate of that transistor there is also going to be sort of small, right? Just because of the capacitive divider right there. Okay, so we probably don't want to make that too small, but we'll see in a second sort of how big we might really want to make that. What if we make these really big so that we get the complete feedback signal going back here? Now, if we said we don't want it to be small, well, then let's make it big. Well, if we make it too big, then now we're actually going to be paying a penalty of basically loading extra cap on the output of our amplifier right here, right? In particular, if I made these sort of like infinitely large, right, then basically these would become the complete loading on the differential side of our amplifier. Okay? So the trade-off here is basically how big do we make them in order to get sort of good gain here versus how much extra loading are we introducing at the output. Now again, maybe you would have needed some caps in any case for noise standpoint. So as long as you can sort of just move some of that over, maybe that's not such a big deal. But eventually, obviously, if you have more cap on this than you wanted over here, that's bad news, right? So let's just maybe kind of quickly run through just some numbers to give us an idea of, roughly speaking, how much gain are we actually going to need in our common mode feedback loop. Okay? So in order to do that, what I want to actually point out is basically what that gain is relative to the gain of the amplifier itself. Okay? So let's maybe just walk through it really quickly. So if this is my common mode feedback loop, just at least at DC, well, not DC, but at, at frequencies where I can really just look at this thing as being a capacitive divider from there to there, what is the common mode open loop gain going to be? At least what are the components that are going to be inside of that? Well, let's just start out. From there to there, what did we say? Sorry, just to be clear. From here to there, what did we say that gain was going to be?
Over CCM plus.
Yeah, that's just kind of like the gain of our sensor, right? So that's CCM over CCM plus CGS. Okay? So that's going to tell us how much common mode voltage change is sitting right there. Okay, what's that going to get translated into?
A current.
Yeah, it's going to get translated into current, right? So that's like the GM of the tail transistor, right? Okay, then what is that current going to flow into? To get back to this point, or really to the common mode point at the output.
The input devices.
Yeah, so it's going to go through the input devices, and then basically flow into the output. So essentially, whatever the output impedance is, that's what it's going to flow into, right? Okay, so now here's an interesting question. How big is this whole thing going to be relative to the actual gain of the amplifier? Can we say anything about the relationship between this thing here and the actual gain of the amplifier? Are those two related to each other at all? And by the way, when I say the actual gain, I mean the differential gain, of course. Any relationship there?
It'll be a ratio of the GM of the differential transistors to the GM of the tail transistor.
Yeah, exactly, right? Because guess what? I've got 2 times IL flowing through here, and I've got IL flowing through each one of the differential transistors, right? So in fact, I could actually say that the common mode gain is going to be that sensor gain times the differential mode gain times the GM of the tail transistor divided by the GM of the input devices, right? By the way, I claim that actually that expression right there should be very familiar to you from, for example, some noise calculations we did before. So, can I even simplify this a little bit further? Or maybe, translate it into some other design variables that we like to use in this class? Yeah, V stars, right? So in fact, I could even say that this is really the V star of the input devices divided by the V star of the tail devices times 2, simply because there's twice as much bias current flowing through the tail device as there is flowing through the input devices. Okay? So in other words, my common mode loop gain is going to be the gain of the sensor times the differential mode gain times this sort of ratio here, right? Which, ballpark, by the way, I mean, maybe that's going to be like a factor of 2 or something like that. So now, here's the interesting question. What's going to set how big of an open loop gain we want for that common mode feedback loop? How would you decide what that value needs to be? How do you decide if that needs to be 10, 100, 1,000? How do you know?
Static error. How much
Okay,
error?
static error on the common mode, right? So what you basically need to know is how big of a static error can you tolerate at the output of this thing on the common mode? Okay, so now let's actually ask you guys. Microvolt of common mode error, do you think that's going to cause a problem? By the way, just to be clear, this is, let's say, in our technology, and we've got a 1.2 volt supply over here. So if I tell you there's a +1, -1 microvolt of error right there, do you think that's a problem, or probably not?
No.
Probably not, right? Okay, let's go up by 3 orders of magnitude. How about a millivolt? Is that going to be a problem, or probably not? Probably not, right? Okay, how about, let's say, I don't know, 100 millivolts. Yeah, now I'm starting to worry a little bit, right? So ballpark, I mean, obviously this is not precise here, but ballpark, you know, if I said maybe a millivolt is okay, and I have a 1 volt supply, and I'm worried about stuff sort of bouncing around all over the place, that probably means I need a gain of about 1,000 or so, right? So that's actually kind of good news. Because it says that if I already had a pretty high gain amplifier on the differential mode to begin with, then maybe actually I can tolerate a reasonable amount of attenuation through that capacitive divider and still get pretty close to the common mode gain I wanted in the first place. Right? So even if this attenuates by, let's say, about a factor of 10, if I had a gain of 10,000 in the amplifier anyways, maybe that's actually not so bad. Right? Now again, I'm really just sort of throwing out some example numbers here, because obviously you really need to figure out what is the precision that's required on that common mode output. And then based on that, you can decide what the common mode loop gain really does need to be. Any kind of questions on this, or? Okay, so I think we'll finish up with this on Thursday, so I'll see you guys then.